It's kind of amazing when you realize that nature has already solved some of our biggest engineering challenges. Today, we're diving into a perfect example of that: how the owl became a master of stealth, and how we're borrowing its ancient secrets to build the quiet drones of the future.
Okay, so let's just get right to the heart of it. The difference here is absolutely staggering. An owl in flight. It's making less than 15 decibels of sound. That's literally quieter than a whisper. Now, compare that to your average drone, which is buzzing away at 60 to 80 decibels. That's as loud as a vacuum cleaner right next to your ear. This huge gap is what this whole story is about.
Which, of course, leads us to the big question. How on earth does an owl pull this off? What is this silent secret that nature's been hiding in plain sight? And, the most important part, can we actually copy it?
To really get why this is such a game changer, we first have to talk about the drone's loud problem. Because right now, noise and inefficiency are the two biggest things holding UAVs back from truly taking off.
And here's why that's such a big deal. That high acoustic signature, that loud buzzing sound, it's not just annoying, it seriously limits where and when drones can fly, especially in our cities or when they need to be discreet. And at the same time, they're just not that energy efficient, which means shorter flight times, and that really puts a cap on what they can get done in one go.
So that brings us right back to our inspiration, the owl. Let's start peeling back the layers on nature's solution by taking a really close look at the incredible design of an owl's wing. It is an absolute masterclass in aerodynamics.
And what's so cool is that the secret isn't just one thing. It's a combination of three brilliant features all working together in perfect harmony. You've got these little serrations on the front edge, soft fringes on the back, and this amazing velvety surface right on top.
So first up, those leading-edge serrations. The best way to think about these is like a tiny comb on the very front of the wing. As the air hits it, this comb breaks up the big, noisy pockets of air into much smaller, much quieter little swirls. It's basically smoothing the air out before it even gets a chance to make noise. Then you move to the back of the wing and you find these trailing edge fringes. This is basically a built-in silencer. It's this soft, porous edge that lets the air flow off the wing super smoothly. It prevents those sharp pressure waves, which is what creates a lot of the sound, from ever really forming. It just diffuses everything.
And for the finishing touch, you have the surface of the wing itself. It's covered in this downy, velvety material that works just like the acoustic foam you'd see in a recording studio. It just soaks up any leftover sound energy and dampens vibrations, catching any noise the other two features might have missed.
Okay, so we know what makes the owls so quiet. We've got the blueprint from nature. The really hard part? Figuring out how to translate this biological magic into something that we can actually build and engineer. This is where the real work begins.
And this is where it gets really interesting. Scientists have looked at these features before. Sure, the serrations, the fringes, the velvety top, but they've always studied them one by one, in isolation. Nobody has ever put all three of them together to see how they work as a complete system. That right there, combining them all, that's the critical gap this project is trying to fill. So that's the mission, plain and simple. To be the very first to design, build, and actually prove that a UAV wing with all three of the owl's tricks integrated together can work in the real world.
And the targets they've set are pretty ambitious. First up, they're aiming for a noise reduction of at least 20%. Now, that isn't just some random number. A drop that big would actually bring drone noise down to levels that meet the World Health Organization's guidelines for cities. That's huge.
But being quiet is only half the battle. The second major goal is to boost the wing's efficiency by at least 12%. What does that actually mean? Well, it means you get more lift for less drag, which translates directly into longer flight times. So the drone is not only stealthier, it can stay in the air longer. It's a total win-win.
So how do you actually do something like this? Well, not with guesswork, that's for sure. You do it with a really careful, four-phase plan that will take this idea from a computer screen all the way to a physical, flying prototype. And look, this is not a quick weekend project. We're talking about a serious, multi-year scientific effort. It all kicks off with creating this massive digital database of owl wings, then moves into super complex computer simulations to validate the designs, then to actually building the thing, with flight tests scheduled for around mid-2027. And the technology they're using to pull this off is just incredible. I mean, they're using micro-CT scans of actual owl wings from museum collections to get the geometry perfect, then running it all through powerful simulation software.
And to build it, they're using advanced tech like 3D printing and something called electrospinning to create that velvety surface.
All of this amazing science, all the simulations and prototyping, it all leads to this one moment. The moment of truth, the flight test. This is where the rubber meets the road and the design has to prove it doesn't just work in a computer, but up in the air. And the testing is going to be incredibly rigorous. They're building a special drone for this and will surround it with a 64 microphone array to create a perfect 3D map of its sound. They'll measure every bit of power it uses, but here's the most important part. They're going to test it side by side against a normal drone wing, so they can show, with hard data, exactly how much better it is.
So what's the end game here? If it all works, the result isn't just one quiet drone. No, it's a blueprint. It's a whole new way of thinking about wing design that could kickstart the next generation of silent, efficient UAVs.
So let's just zoom out for a second, because this is where we talk about why all of this really matters. What's the real-world impact of cracking this code? Well, the possibilities are pretty mind-blowing. Imagine package deliveries showing up at your door that you barely even hear. Or think about drones that can monitor endangered animals and delicate ecosystems without stressing them out. We're talking about a future with less noise pollution and brand new ways to help with conservation.
You know, the lead researcher on the project, MMHK Supto, put it perfectly. He said, this work is all about bridging the gaps between the worlds of biology, the science of sound, and aerospace engineering to create something totally new.
And really, that just leaves you with this one final, amazing thought. If the key to building a better drone was hiding on an owl's wing this whole time, it just makes you wonder, what other incredible, revolutionary ideas are out there just waiting for us, hiding in plain sight in the world all around us?